All right, hi everyone. Thanks for coming out through the pouring rain. It's my first time in Amsterdam. It's a place I've always wanted to visit. It's very exciting, and I've had a few people be like, oh, it's not the right time of year to come, but luckily I'm from Vancouver where it rains all the time. So I'm very used to it, feels very, very much like at home. So my talk's called The Tyranny of Structurelessness, which is a bit of a mouthful. The core idea here is that we like structure and we don't like things that are unstructured, obviously. There's this classic quote from Dijkstra, who most of the people in this room probably know who he is. He's from not that far from here, that the quality of a programmer is in decreasing function with the number of GoTo statements that they use. Which may be a strange quote to start with, which is basically a burn on all the programmers from when he was active in the 70s and 80s, and actually took about 25 or 30 years for people to really come around to this idea. And I've, in fact, recently had an argument that I had to invoke this with as well. So it's still around, it's still doing the thing, but we don't have go-tos in Elixir, so why am I even bringing this up? And we'll get there in a little bit. So my name is Brooklyn Zelenka. I'm XP'd everywhere on the internet. I'm the co-founder, CTO, chief scientist at a company called Fission. We're a small team, about 5 people. I'm based in Vancouver, Canada, but we have the closest person that we have is nearby in Belgium. You can find us at fission.codes, and our goal is to make DevOps and backend coding obsolete, which makes it kind of maybe not a popular opinion with this particular crowd, but I assure you that Elixir fits into that future as well. To give you a rough idea of the sorts of things we're doing, we're working a lot with primarily distributed systems, CRDTs, the interplanetary file system, and decentralized identities. If you want to hear more about that, I'm actually giving a talk at a meetup tomorrow night. And you can ask me a little bit about that after if you're interested. I'm a programming language theorist and virtual machine enthusiast. I used to do, if you're familiar with the Ethereum project, I used to work on improving the virtual machine for the EVM. And the reason that I am speaking at an Elixir conference, other than I did Elixir for a number of years and taught it, et cetera, is I'm the primary author of a set of libraries. The main ones people know me for are Witchcraft, which is porting the Haskell standard library into Elixir, and Exceptional, which is a error handling DSL. Also, if you're a sticker person, I have stickers. Feel free to come grab them after the talk. So, the big idea. At a very, very high level, we should be working at a higher level than people are today in, I think, most languages, but especially in Elixir, where we have so much more power than people really take advantage of. There's a few libraries that do this, but most application code tends to just follow the layout and the pattern. If we look at the design of the language, and really any language, it's the designer's intention and the needs that are really coming across, right? So Google created Go. Rob Pike, the lead designer for that project, has said that the purpose of Go is to be familiar to programmers coming straight out of school so that they can be interchangeable, right? So that you can hire in another 500 programmers and get rid of them when you don't need the project and sort of move them around. And there's a few side effects of that, one being that you need you've pushed the complexity from, you have this very familiar, simple code, but you've pushed the complexity into the large, right? You can never actually get rid of complexity. Erlang, developed by Ericsson, really to do telecom, happens to be a really nice fit for the way that history went with the internet, but didn't really catch on in the sort of post-Rails world until Elixir, which was really built for doing web applications, real-time, and chat, which is what most things that we're interested in doing today, and with a slightly different mindset around open source and collaboration. So whose organization looks like this, where you have a architect or a design document or something that goes down to all of the programmers, and then the programmers take that and execute in the code. Just kind of roughly show of hands. Cool, like 4 people. Which is fine. Some organizations, that's exactly what you need. Most people, or I'm assuming at least, looks a little bit more like this. I think I get more of a show of hands for that one. Yeah, like 90% of the room. In this scenario, you have to worry a lot more about how can we communicate with each other. The code that I write now, I have to think about in 3 more months and come back to and understand again, right? I shouldn't have to understand the entire stack to edit a piece of code. It should just be semantic. And beyond that, as time goes on, we want more out of our code all the time, right? And not just out of our specific application, but the users want more things from features as well. So the complexity grows faster than linear, right? What we want today and in 5 years is the delta is huge. Because of that, we have to find new ways to reason about our code at scale, right? When you have an application that is 100 or 500 lines of code, sort of the hello world style, that's very different than when you have 10, 100, or 1,000,000 lines of code. Are the patterns that we use today the best possible patterns that we'll ever have? Obviously no, right? GoTos were the absolute bread and butter in 1970, and they aren't today, and there's a good reason for that, right? So how will we write our code in 2020, which is in a month, 2025, and 2050? And what I'm proposing is that we switch our focus from the mechanics of a language to domain and structure. And let it evolve kind of like how we've evolved from the original Erlang days to modern Erlang and Elixir to some magical unicorn future where we have all of these things. So let's think about code starting in the large and then slowly zoom down after that. So the code that you used to write is imperative, right? You were in, say, JavaScript or Ruby or whatever. And we live in an imperative world. You don't have a choice but to do side effects, right? I'm giving a talk, this is changing the world. Maybe the talk itself isn't changing the world, but it's making changes to the state of the world, right? So you can't actually get away from having imperative code, right? It's not possible. The way that people say is to write, quote, good Elixir, is to have a functional core imperative shell. So you do all of your pure functions and pattern matching and all that nice stuff, and you keep that as little helper library functions, and then you compose them together and do all of your side effecty bits as well, right? And we have this nice separation. There's one more layer that we can add, which is a semantic DSL layer. Matt Parsons in the Haskell community calls this an object-oriented layer because you can have a description and have them almost inherit patterns from each other as you go down. But placing this interface in between the imperative and purely functional code helps for a few reasons. And to sort of bootstrap the understanding really quickly before diving into for literally the rest of the talk, if anybody's heard of a hexagonal or 12-factor app, right? Famously, used by Heroku or other sorts of systems. This is a generalization of that pattern, right? We should have some interface that separates out our code and that we can talk about in this DSL. The other thing that we get, so that's just abstraction. If we make our abstraction structured, we get a few more things as well. So if you start focusing on the properties that make up your code, so that it's, say, associative or commutes or that timing doesn't matter, right? You can property check your code And now if you have a protocol in between the actual implementation, you're building your DSLs off that, you can do model testing. So instead of having to test your entire distributed system with all the different gen servers and actors and all of this stuff, you can test it on a map. And because they have the same properties, you know that the model reflects the more complex system. So let's get back to that original quote, GoTo is considered harmful. What exactly is wrong with having so much control, right? The low-level primitives that you have are very, very powerful, right? They give you as much leeway as you want, but they're also a really incredible foot gun, right? So GoTo's low-level instruction, it's what the machine's going to do. It's when your code compiles, that's what is actually going to happen on the hardware, right? Very flexible. You can do all kinds of tricks. Get your code really small, get your code really fast, right? It's highly concrete, but there's a huge number of implicit states. So if this is a little 6-line program and line 5 has a GoTo on it, you go from one step to the next, and then we could really end up anywhere in the program after this. In fact, we could end up outside of the program, which is a seg fault, which we don't want runtime errors, right? So that's no good. So the solution to this is to add more structure to our code, right? We're reducing the number of possible states that we have to think about by adding some structure, some subroutines, loops, branching, named functions, all of that stuff. And that's sort of the beginning. This was deeply controversial initially, right? And that's a first step along a broader spectrum. So, of course, functional programming gets us some other structures, some other benefits, right? Map, reduce, filter, all the classics. Identity function even, so that you can stub out parts of your application. Map is actually kind of a strange one in Elixir because mapping for performance reasons pushes everything, the whole enumerable or enum module pushes everything down into a list because that is implemented natively. And then you have to go and put it back into the data structure. Obviously, there are trade-offs, as with everything, right? It depends, but the advantages you get outweigh the disadvantages as your code grows. So you're exchanging granular control for structure, being able to reason about your code, both in the small and at large. It's more concerned with the humans on your team than with the machine. It's much safer because you're ruling out the cases that don't do the kinds of things that you want them to do. And this exists on an entire spectrum, right? So if you have all these low-level instructions and you're working with a Turing machine, you can easily end up in the Turing tar pit. But that doesn't mean that you can't end up with this in map, filter, and reduce. You absolutely can, right, in church chasm. And then kind of partway along this too, if you go to category theory, you end up with Haskell fanfiction, which is basically what I wrote with witchcraft, right? You need to keep that structured as well and build other structures on top of this. So these exist on a spectrum where DSLs are on one far extreme and a Turing machine on the other. Big complaint about structured code is that it requires a little bit more boilerplate and a little bit more setup up front. And the complexity over time doesn't seem to really work out, at least initially. But what happens as your code grows is if you're doing things with these small pieces that aren't designed to necessarily work together, you have this explosion of complexity over time. Structured code grows, the complexity grows sublinear, right? We have a logarithmic complexity. And so your large code base becomes much easier to refactor, to think about, and to read and understand. If you've ever used Elm, this is what they do as well. They have a bit of setup, a bit of boilerplate, but it becomes very flexible and easy to work with in a large code base, right? So you have to learn a few more things, a little bit more structure, a few more concepts, but you get the payoff in the long run, which isn't great for a hello world example, but really does help you when you're trying to ship software. So I've been throwing around this term complexity a lot. Challenge I run into when I talk to people about complexity is it doesn't mean what they think it means often, right? We like to think complexity bad, simplicity good. And yeah, there's a bad kind of complexity. It's really complicated code, things that are an unstructured mess, quote unquote. We've all seen that code before. We've all written that code before. I certainly have. The good kind of complexity is when there's some sort of deep connection, right? Where you have a small number of elements interacting to create a large number of possible states. So it's very powerful, but not an infinite number of different elements being sort of thrown together, right? So all of these here are the golden ratio, and they're all very sort of different versions of them. In fact, this is also a version of it, right? But there's some common thread, and we can understand them all quite, quote, simply. The core idea to that is orthogonality, which is a term that not as many people are familiar with. So I have a nice little visual metaphor for you. We have two lines with some regions on them, right? Completely disconnected, and we can think about them independently. If we connect them together, suddenly these independent regions can talk about points in a two-dimensional plane. We can draw figures. We can make those quite complex. We can add color and time. And now we have animation. We have literally everything that you see on your computer screen. With 4 structures, right? 4 dimensions to this, with an effectively unlimited number of states that we can produce. But we can think of each part independently. So complex is not complicated. It's interconnected parts. Complicated, it means that it's hard to understand. Actors are really nice, but actually kind of low level. Every step is very simple. A lot of people have talked about it as being like an organism, right? You have all these little pieces, and each piece is really simple, and they interact like this. The problem with organisms is that they're very, very complicated in the large, even if each step is very simple, right? It's just chemistry. In the large, it becomes very, very, very complicated. And this is a situation that when I was doing consulting, I would run into all the time. People would just throw a gen server at it, and another, and another, and another, and now they have this unbounded complexity. So what do you do about that? Good interfaces are not necessarily good abstractions. Gen server is a fantastic interface, right? But it has 0 semantics. It just says that there's a point in memory over there somewhere that has an interface that you can interact with, right? I was talking to some of the Elixir people at my company, and they were saying, yeah, every time I use a gen server, I reinvent the wheel every time. I'm always coming up with the same abstractions over and over and over again, and I wish I just had one way to talk about these topics without having to, it just seems like a small thing. Well, then they should go and ship a library that helps people do that thing in a more semantic way. But we're going to look at one common example. Just a key value store, right? I mean, only have a 40-minute talk, so we're going to keep it very, very simple. So we have our interface here is to initialize one of these, to get a value and set a value. This is on map, right? So it's a protocol on map. We can initialize it. We're using a proxy, so we just say, give me any map, and I'll make sure you get an empty one. You can get a value out of it with map.get, and you can set one with map.put. Right? Very straightforward. This is an async version, right? So we have to write the map portion of that. This is a process database with a struct that just holds the PID inside, just to keep the reference to it. And then we're going to abstract that all away with the protocol, right? So we still have get, we still have set. In fact, we are inside of this going to just have an agent with a map, right? But we want to have this running in some sort of distributed context. Looks pretty straightforward, right? So we can now get and set these using those, and we have the same interface as we did on just a plain map. It works the same way, right? We've encapsulated all the detail. We don't have to think about what's happening inside the gen server anymore, right? It is effectively a map, right? Somebody who wants to come and use that code doesn't have to worry about, is this async or just a regular map? They can use it in the simpler case, right? Our entire focus becomes this interface. So abstraction and DSLs. Not getting trapped in the details. I know that I'll have at least one person in the audience who agrees with me. I was talking to the MC right before, who has written a DSL for doing chatbots, right? That is not the kind of thing that I want to have to do in concrete code all the time, right? I think everyone's application should be DSLs. So there's a lot of code that has commonalities, right? This is 3 ways of writing the same thing. Obviously, they have a different amount of power to them, right? The map version is extremely powerful, right? Actually, these two have roughly same expressive power, but in slightly different ways. But they're both more powerful than a list, right? They're all enumerable, even though they all get turned into a list at some point. In witchcraft, we just, as a side note, we don't convert things into a list. We always convert them back into the original structure in the same order as a property that we're only updating the elements in the structure, as opposed to some kind of iterative thing where you're saying, I'm going to turn this into a list and then iterate over them. So these are all functors or enumerables, depending on how you want to think about it. Also, these have similar structure too, even though they're functions, right? Again, we have a straightforward version and then some async version where we have to start thinking about or not worrying about ordering or any of those things. And this example is not very pipeable, right? Because in both cases, there's two branching paths that are happening during the code that you have to bind to some variable names. It's a lot of duplicate code between the two of these, right? And there should be a better abstraction for this, which we'll look at the very end. But just for right now, this applies to both data and functions. So the way that we abstract this away is we start with the rules. What do we want the overall solution to look like? And then we need to think about how it's going to get run contextually, right? So this often is a protocol. It doesn't have to be, but very often is the case. Thinking in this way is always a two-phase process. You have to think about the concrete version of what you're trying to do, abstract it, and then as close to the application boundary as you can get. In that imperative ring, do the concretion. Right? We never want to push that into our code. We want to work only with abstraction inside the purely functional code and the semantic DSL. With that in mind, let's do a little bit of improving on the kernel, on the standard lib. So we're going to do fallback keys and bang functions in a more orthogonal, principled way. Right? So orthogonality is the fundamental piece for good composition, right? Things that will work with many different things. Here's map.get today. Right? Works the way you'd expect it. There's this default value that you have to pass in. It defaults to a nil. You know, I have other feelings about that part. That's fine. But why do I have to even remember in this second case that this here is a default value? The number of times I've had to go to the documentation and see, oh, right, this is a different arity. So in this case, this argument means this thing, right? It should be more readable than this. So here's a fallback function that does the exact same thing. If it gets a nil, we give the fallback. Otherwise, any other value, just return the value. And now you can do a map.get that is always 2 arguments and pass it this fallback function. It's very readable, right? We understand that this is a fallback. And it also now works with lots of different kinds of things. We can now use this on list first, which also returns a nil. And we can get a fallback from that too, right? With this one little refactor, we've gained a lot of power from one abstraction. Right? It's also more focused. I can test this really easily. I don't have to test 6 different versions of it, right? The principle at play is that I have something that gets a map, it has an interface that gives me a nil, and I can test that on its own, and I can test the fallback on its own, and not have to worry about the interaction of them all the time. And yeah, ad hoc function extension. This is a way of doing something like a protocol without having to resort to the protocol itself. Let's look at bang functions. So you have 2 variants often. You'll have one with an exclamation point and one without, and the one with the exclamation point actually raises an error, which is a side effect. It unwinds the whole stack, all of that stuff. Why am I worrying about having these 2 versions, right? So this is what exceptional does. So without getting into how we do this kind of thing too much, let's just assume that you have a safe map that always returns the error struct, right? Because exceptions are regular structs with an extra couple keys on them. That's all they are. And then a couple helper functions to say, is this an exception? So you can return it as just a regular value. We have a helper function ensure with the bang that makes it so that you can pipe into it and then say, actually raise this thing if it's an error, otherwise continue. And then a few little helper DSLs for doing piping, because this is the sort of thing that you want to pipe a lot of. So if you have this little squiggly arrow and a regular value, it does the normal thing. Otherwise, you will skip it completely and just return that initial error as you go. And if you want it to be the point where it explodes, you can give it the 3-arrow version. So now you can have an entire chain of functions and know very clearly, just visually, where the dangerous part of the code is, where this might actually raise as opposed to something that I can handle in pure code. Right? So this works everywhere, any data flow, right? It's super easy to test because now you don't have to stick a rescue around your test code or assert anything about it. You just say, what's the kind of error I'm getting? Oh, it's this struct that I'm getting back. You can also stick that in your type definitions too. And as a bonus, we don't have to worry about nil anymore. Is this an actual nil or is this an error? Because we know that we're returning some kind of exception struct that has these special keys on it. Touched on this a little bit on the last slide, but I wanted to really underscore it. Metaphor is really important. We only have a certain number of operators in Elixir, so fine, don't go too wild with them. But flow is very important in Elixir, right? So this is that case I was saying before, where you can see very clearly this is a regular pipe. This is piping something that may contain an exception, and this last one will actually raise the exception if there is one, because I'm going to need to assume after this point that there's some, that this works without an exception, that I'm getting an actual value. There's some kind of guard on it, right? These are intended to be clear, composable, and have a high degree of reuse, so that we don't have to think about all the different possible places and re-implement the same patterns everywhere. We can just take code patterns, unlike in OO. In FP, we can take code patterns and enshrine them directly in code, and then use them as a library, right? So we should be doing that a lot more. We give users choice, right? I don't have to wrap functions in a rescue block and then get back the value anymore, or have to write my own version that doesn't raise. You get, the end user has a choice of how they want to deal with that error case. This makes it much more testable as well. So you can just use literally isException, and it'll tell you, did you get an exception back? And you can still add a protocol on top of this to get even more generality. And we want our code to read like a story, right? So if we have these nice abstractions and we can pipe them through and flow, we don't want to worry about the mechanics as much, which is kind of more like this, but it still gives you an idea of I'm doing this, then this, then this, then this. And it's very easy to look at, understand, and just see, this is what Phoenix does, right? At a high level. We should be looking at things at a high level and only zoom in to the degree that we need to. So we need to sort of eat the elephant one bit at a time, somehow, right? So we're going to try to do refactors, or even writing a new application. It's kind of in this new style. Do we do it by feature? Do we do it by behavior? No, you do it by structure and properties. And actually taking a step back and looking at what are the properties in my code. So what do I actually mean by structure? There are 3 right answers to any question. It depends. Why not both? And because math. And structure falls quite squarely into the 3rd one, right? Which I would say is the best answer, because you can actually back it up, right? So associativity, right? It's not a data structure. It's not a function. It is some set of rules about how your code's going to work. It's an interface and rules. Basically, we're saying we don't care where the brackets are going to go. It's going to do the same thing. If you like a visual version, it's like this, which is, again, really nice fit for Elixir, because we have this flow metaphor again, right? We can box these 2 together, or those 2 together, and we get the same end result, right? So this is a protocol semigroup from Witchcraft on integers in the simple case, right? We just have addition, or for lists, we can do list concatenation. And there's some common bit of structure here. These are things that we can always add more to. Think about a logger, right? Or a CRDT. They all have this property. We should always be able to just throw more data at it and have it get recombined. You'd think that this exists on basically everything, but unfortunately you have to prop check it and make sure. Because, for example, division doesn't work this way. Depending on the way you place the brackets, right, you'll get a different answer. So you really do have to think about the properties and the counterexamples in your tests. Composing properties, you often run into a situation where you want several of these. So you want it to be both, let's say a CRDT, for example. You want it to be both associative and commutative, right? You don't care which way the brackets are going to fall, or the order that things are going to happen in. You want eventual consistency. You have a few options. One is keep it straight in your head, put it in the docs, and I'm just going to plug type class really quick. This is one of the dependencies on Witchcraft, where you can say, in order to define this protocol, this other protocol must have already been defined for this data structure. So you can have the macro help you with this too. So let's do something fairly wild with this. Let's say that we want to do parallel composition of pipes, right? So that case I was saying before where there's two paths through the code. Concurrency is a partial order. So over time, we have events, and they'll kind of be arranged more or less like this, right? This blue dot, or blue event, is going to happen somewhere, at the same time, quote, same time as the things on the left, which means it might come in this order when we linearize it, when we look at the actual wall clock, or it might be in these orders, or actually in a large number of other states where there's some that are happening at exactly the same time. But orange always happens before purple, red always happens before blue, it follows this kind of a structure. All loops or other structures like that have to become linear, right? We don't have cycles in this. This is a directed acyclic graph. So we want to have serial composition, parallel composition, and be able to have explicitly, because we're doing abstraction, right, an explicit evaluation strategy for this. We want to be able to say, give this to me in a single-threaded fashion, or do this over, distributed over geography, or just on my system and spin up a bunch of gen servers and make this work, right, without having to worry about the detail. Or you'll have to write the detail at some point, but the high level, we don't want to have to worry about it. So this gets us back to these nice pipes. This is, again, witchcraft syntax. So this here is function composition. So it's laid out like this, and here is the code that goes with that. So we're going to have some input value. It's going to split into these two functions. That will then, this top half will also be split, etc. One of the properties is that it doesn't matter which is on the left or the right, or the top and bottom in this case, right? I should be able to put the blue at the very, very top as long as that line is in parallel with the purple and the orange, right? Here's a DSL on top of that because, the church chasm. We're too far in the weeds when we're using function composition directly, right? We should be able to just pipe some things together. So we're going to say split. Here's my two functions, in my little do block. Unsplit at the end, so that's a merge, and then unsplit the whole thing together. Right? So this gives us the same thing, but written in a more understandable linear fashion. There's the layout again. Often with this kind of thing, you want to break it into two halves. You have the plan that you're going to execute, which you often want to put in carrier data, so some data structure that you're then later going to evaluate. Here's again the same structure. The programmer should never have to worry about this part except for when initially writing the library that does this, right? Here's our splits and unsplits, and this gives us the, our sort of DSL abstract syntax tree. And then we can put a protocol on top of it called data flow, which just gives us the split and unsplit, and everything else works as you expect in Elixir. So here's the default case for any. By default, we will just stick them in tuples and then evaluate them in a totally linear way, and then combine them, just passes it to this combining function, this combine by at the end. So here's an example of what that looks like, right? That's the example from before. And in fact, this code will always look the same no matter the evaluation strategy, because we'll have different protocol implementations. Here's the async version. And this is just getting pushed into task.async just as a simple example. And again, this part here looks the same, right? The difference is we've added this asyncify that then pushes it into this async structure. So we end up with this very high semantic density, right? We can talk about this totally linear data structure. We can inspect it directly. We have declarative configurable data flow, right? You don't have to say all the time this is going to be in directly, executed in line, or we're going to push this over Broadway, or whatever, right? It's totally configurable. You can also pipe one of these in say, the distributed case into stream, and then the next one can be into, just the regular linear one, right? You can have the caller, you give them all of the ability, the flexibility to still say, take this thing, I understand how it works, it's this, this graph, and do it in this way at call time. This is also model testable because we had those properties in advance. So if you do prop testing on all of your implementations, then you can take the simple one and test that one. And yeah, I mentioned you can change the evaluation strategy as you're going, as you're piping through. So a call for libraries in general in this style. I would love to see more. I was giving a talk about Haskell at the beginning of the month, and realized that I would like to actually see some of this stuff taken further in Elixir. So things that you can plug into and extend and test in a single-threaded context, but use in a distributed context or some hybrid. Railroad programming, which you get with exceptional today, I would like to see available in a distributed context, because doing error handling, async error handling is very difficult, right? So if we can do this in some sort of principled way, where it looks kind of like this, which is what, in fact, exceptional does, but to do it over some distributed setting would be very, very helpful. And doing distributed logging as well, or, again, doing single-threaded logging too in the same interface, never having to worry about it again. There's actually a surprising amount of complexity in this case when you start digging into it. So I'd love to see somebody tackle that. In summary, for doing domain-driven design, please use more protocols. Let's have more abstraction. Add a semantic layer. Locally test your distributed system without having to set up the entire thing. Understand under which conditions your code works and which it doesn't. Right? Say that we have an explicit assumption that order doesn't matter. Right? And let's be clear about it. Prop testing is so much more useful than unit testing, because you're testing a large number of cases. And all of these things should make it so that you can code half asleep. Thank you, Amsterdam.
Thank you.